Hi everyone, my name is Brooke R, and today I'm going to be talking about ionization energy, a key concept in chemistry that explains how atoms behave when they gain or lose electrons. It's super important for understanding reactivity, trends in the periodic table, and even real-world applications like scuba diving. So, let's dive in. Let's start with the definition. Ionization energy is the amount of energy required to remove one electron from a neutral, gaseous atom, forming a positive ion. In simpler terms, it's how hard it is to pluck an electron off an atom. If it takes a lot of energy, the atom holds its electrons tightly. If it takes less, then they're more loosely held. Now that we know what ionization energy is, let's look at the trends on the periodic table. There are two major trends that you need to know. Down a group, or top to bottom, ionization energy decreases. That's because as you go down a group, electrons are farther away from the nucleus, and there's more shielding from the inner electrons. This makes the outer electrons easier to remove. Across the period, or left to right, ionization energy increases. That's because the nucleus has a stronger pull on the valence electrons, holding them more tightly as you add more protons. So it takes more energy to remove them. This diagram helps visualize what I just explained. Notice how the ionization energy increases from left to right and decreases as you move down. This pattern helps predict the chemical behavior of different elements. Now let's talk about successive ionization energies, the energy needed to remove more than one electron. It usually gets harder and harder to remove each additional electron. After you removed the valence electrons, the next electrons are much closer to the nucleus and held more tightly. This is why there is often a huge jump between, say, the second and third ionization energies in some elements. You're moving to a new, more stable electron shell. This graph shows you what that looks like. The energy needed increases gradually, then spikes. That big jump usually shows when you've taken away all the valence electrons and are now trying to remove the core electron, which the atom really doesn't want to give up. So how does ionization energy relate to the real world? Well, one great example is scuba diving. Divers sometimes use a gas mixture called HELOX, which is helium and oxygen. Now you may be wondering, why not just breathe normal air? Well, at deep depths, oxygen can become toxic in high concentrations, and nitrogen can dissolve into your blood, causing decompression sickness, also known as the bends. Helium has a lower solubility than nitrogen, which means fewer gas bubbles form in your blood when you surface. But here's where ionization comes in. Oxygen has a relatively high ionization energy, meaning it's less reactive than some other gases under those high pressure conditions. That makes it a safer part of the breathing mix. So thanks to ionization energy and the understanding of atomic behavior, scientists have created safer breathing mixtures for deep sea divers. There are a few key factors that influence ionization energy. Atomic radius. When atoms are larger, the outer electrons are farther from the nucleus and easier to remove. So ionization energy goes down. Nuclear charge. More protons means a stronger positive charge in the nucleus, which pulls electrons in tighter and increases ionization energy. Electron shielding. Inner electrons shield outer electrons from the full pull of the nucleus. More shielding means lower ionization energy. And finally, electron configuration. Atoms with full or half-full shells, like noble gases or elements with stable subshells, tend to have higher ionization energies because they don't want to lose that stability. So how does ionization energy relate to reactivity? Metals, like those in groups 1 and 2, have low ionization energies. That means they give up electrons easily, which makes them highly reactive, especially with nonmetals. Nonmetals, like oxygen or fluorine, have high ionization energies, meaning they hold onto their electrons tightly. They're less reactive in terms of losing electrons, but more reactive when it comes to gaining them. Understanding ionization energy helps explain why sodium explodes in water and why helium just sits there. Now, let's do some practice problems. Which of the following atoms would be expected to have the largest ionization energy? Sodium, magnesium, or aluminum? Pause the video if you need more time to think. If you said magnesium, you're correct. Magnesium would be expected to have the largest ionization energy of the three. If you got that question right, skip ahead to the next practice problem. Otherwise, stay here. Which atom has a higher ionization energy, sodium or magnesium? If you said magnesium, you're correct. Again, magnesium has a higher ionization energy because it's to the right of sodium on the periodic table. This is the last practice question. How does ionization energy from an element influence the type of ion it typically forms? Take a second to pause the video if you need to. A higher ionization energy suggests that an element is more likely to form an anion, or gain electrons, rather than a cation, losing electrons. To sum it up, ionization energy tells us how strongly atoms hold onto their electrons. It increases across a period and decreases down a group. Successive ionization energies get progressively larger, especially once the valence electrons are gone. And it's not just a theory. It has real-world uses, like helping scuba divers stay safe. Thanks for listening, and I hope you learned something new about ionization energy today.